In this video, we're going to talk about simplifying, multiplying, and dividing rational expressions. Now, rational numbers are numbers where you can divide a number by a number. You can write it as a fraction. So a rational function is a function with polynomials in the numerator and the denominator. And a polynomial can be written in function notation, like these are, or we can write it with an expression. This is a linear binomial divided by a quadratic binomial. Now, they don't have to be binomials and they don't have to have these degrees. You can have any polynomial you want in the numerator and in the denominator. So, remember, the domain of a function is the set of all possible x values that are real numbers, and the range of a function is the set of all possible y values that are real numbers. So for a rational function, the only value that causes us to break rules that we've learned in algebra would be any x value that does not make us divide by 0. So all real numbers except the x's that make you divide by 0 are going to be part of the domain. Well, in this first example, what is the only value that I could use for x that would cause us to divide by a 0 in this function? Well, if you think about it, I'm dividing by x minus 2 here. So if I put a 2 into this function, I'm going to be doing 2 minus 2 in the denominator, which gives me 0. So I cannot let x equal 2. A quick way to find that out is to write yourself an equation where we take the denominator, x minus 2, and say it cannot equal 0. And you can solve this little equation by adding 2 to both sides and seeing that x cannot equal 2. But how do I write this in interval notation? Because that's what the instructions asked me to do. If I were to graph all of the numbers that are not equal to 2, I would do an open circle at 2 and shade everything else. So my interval notation would go from negative infinity to 2, and then from 2 to infinity. And we use a union there and parentheses because 2 does not count. Now we can do that same procedure with all of these other problems. In the second one, x squared plus 3 cannot equal 0 because we can't divide by 0. When you solve this, you see that x squared cannot equal negative 3, and you may be thinking the next step is our square root, but we can't take the square root of a negative number without getting imaginary values. So here it'd be x cannot equal plus or minus I times the square root of 3. Well, that's not even a real number. So there's not going to be a real number that makes us divide by 0 in this problem. So the domain for this is all real numbers from negative to positive infinity. And the last one, if we do the same thing again, we're setting the denominator not equal to 0 because we can't divide by 0, and we get x squared cannot equal positive 4. Well, if we take the square root of both sides here, we're going to get that x cannot equal positive or negative 2, because if I square either of those numbers and subtract 4 from them, I get 0. So if I were to graph this on a number line, I would have open circles at positive and negative 2, and I would shade everything else. The interval notation for that has 3 parts to it. We've got the negative infinity to negative 2 with parentheses, the negative 2 to positive 2 with parentheses, and the positive 2 to infinity. So you've got to use union twice, and I couldn't quite fit it all on one line. Now let's talk about how you simplify rational expressions. Your first step is going to be to factor the top or numerator completely. In this first example, the degree is 1. I can't factor that. That's a linear binomial, so I just have n plus 6. For the second step, we factor the denominator completely. Here, in the denominator, I do have a GCF, and I can take that out, or factor it out, and I get n plus 6 times 3 in the denominator. Next it says cancel out factors that are common to the top and the bottom. Now here's where we need to talk about what factors are. If I have 6 divided by 12, factors of 6, if I did a factor tree, would be 2 and 3. And factors of 12, if I did a factor tree, would be 2 and 3 and 2 again. Now, I can cancel out factors that appear on the top and the bottom. Factors are things that are multiplied together. So I can cancel out 2's that are on the top and the bottom and 3's that are on the top and the bottom. When I do this, you guys know that 6 divided by 12 is equal to 1/2. Where'd the 1 come from? That's because when I canceled out the 2 and the 3, I have a 1 still left. So don't make that a 0. When you divide, you get 1 when you divide one thing by itself. The 2 is on the bottom, of course, because the 2 is not canceled out. So I get 1 divided by 2. Now, one thing that students will do sometimes when they're simplifying rational expressions is they'll say, well, I've got a couple of things that add together to give me 6 plus 4, and 2 plus 4, and 2 plus 10 gives me 12, so let's just cancel out the 2's because they're added together. That doesn't work the same way as multiplication did. You can cancel out factors that multiply to give you something, but you can't cancel out terms that add to give you something. So in this example that I'm doing right now, I can't cancel out the 6's because they're added. But I can cancel out the n plus 6 and the n plus 6. And when I do that, kind of like you saw in the 6 divided by 12, I am going to have a 1 remaining in the numerator and a 3 remaining in the denominator. So my solution to this simplified is 1/3. Now there is another part to this problem, and it says not only to simplify, which is what we did here, but also to state the domain restrictions. To state the domain restrictions, we want to do that before we simplify. So we're going to simplify or set the denominator equal to 0 even before we start crossing things out. So I have 3 times n plus 6 cannot equal 0. We know that 3 doesn't equal 0, so that's not a problem. But could n plus 6 equal 0? You sure could if n was equal to -6, and I got that by subtracting 6 from both sides. So the second part to my solution is that n cannot equal -6, and those are the domain restrictions here. Now try the others. Factor out a GCF, then factor it if it has a degree greater than 1, and look for any factors that match. Don't forget to state your domain restrictions. So for the rest of the problems, I did the first step in yellow, the second step in green. I found the domain restrictions in blue, and I canceled out and wrote my final answer in orange. One thing to pay attention to is that sometimes you'll have multiple factors, like we did in this problem. You'll have multiple factors in the denominator. You need to set each of those equal to 0 and solve to find the restrictions on your domain before you simplify. So don't forget to do that. Also, in this problem, sometimes there will be 2 steps to your factoring. Here we had to factor out a GCF and then factor a difference of squares. So don't forget that part either. When we multiply rational expressions, we have 2 different rational expressions that are being multiplied together. If you remember multiplying fractions, you can multiply 2/3 times 4/2 and get 8/15. And we get that just by multiplying the numerators and multiplying the denominators. And that's all we're doing here. But once we do that, we want to make sure we simplify also. In my example, we couldn't simplify, but in some of these examples you'll see we can. Another thing to remember is that when you're working with exponents, if you have x cubed divided by x squared, you're just going to get x to the first because we subtract the exponents from top to bottom. So 3 minus 2 is equal to 1, but we don't have to write the 1 exponent because it's understood to be there. Finally, remember that if you subtract and you get 0, like x squared divided by x squared, x to the 0th power, anything to the 0th power, is just 1. So you can just remember that when you divide something by itself, you get 1. And you guys knew that already. All right. So in these problems, it says to factor each expression completely. Then you can cancel the expression from top to bottom or diagonally. And what that means is, in this first problem, notice that I have a b in the numerator and another b in the numerator. So with problems like this, I would likely multiply first. So I get 2a squared b squared, because b times b is b squared, divided by b squared times c times a. Because I have a b squared in the numerator and the denominator, that will give me 1 when I cancel those out. I have an a in the denominator and an a squared in the numerator. So this a will cancel out, but this a squared will still have an a left. I don't have any c's and I don't have any 2's that are up top and on the bottom. So my solution to this one is going to be 2a divided by c. It doesn't say to write restrictions on the denominator here, so we're good to go. Now in the next one, I don't want to take out my calculator. So with the number part, I'm going to simplify those like you guys did back in elementary school. I have a 12 in the numerator, and I can simplify 12 and 36. If I simplify the 12 and the 36, I get 1/3. The 24 and the 8 I can simplify also, and I get 3/1. But now notice that I can simplify diagonally also. I have a 3 up top and a 3 in the bottom. One's purple, one's blue, but it doesn't matter. So I can simplify those also. And my numbers all cancel out, and I didn't even have to multiply them together to discover that that was going to happen. So my numbers give me 1 divided by 1. Now for the variables, I have an s here and an s cubed there. That's s to the 4th. I have a t squared and a t squared here. That's t to the 4th. And in the denominator, I have an s to the 4th and an s cubed. That's s to the 7th. And finally, I have a t cubed and a t. That's going to be t to the 4th. Now we can simplify these by subtracting. 4 take away 7 gives me -3, so s to the -3rd power. And 4 take away 4 gives me 0, so t to the 0 power. Now to simplify, if I have negative exponents, I can make them positive by moving them across the fraction bar. And t to the 0 power, or anything to the 0 power, is just a 1. So my final answer for this one is 1 over s cubed. Now for the next one, this is where we first get into GCFs. So I'm going to factor this portion, and the GCF there is going to be 6. Now I've factored each part of this by taking out GCFs where I could. Now notice I can simplify diagonally. This is on top of one fraction, this is on top of the other fraction, but because they're all multiplied together now, numerators and denominators, I can simplify the m-3 to be a 1. Also notice that I can simplify 9 divided by 18, which gives me 2 on the denominator and 1 in the numerator. I can now simplify the 6 and the 2, giving me a 1 in the denominator and a 3 in the numerator. And also notice that I can simplify the n squared divided by n, giving me a 1 in the denominator and an n in the numerator. So what's left over? This is kind of a mess. I've got a 3, a 1, and an n in the numerator, and in the denominator I've got 1 times 1 times 4. Well, that gives me 3n in the numerator and a 4 in the denominator. Now it's time to try some. Work out each of these problems and see what you get when you simplify them. So here are some answers to those problems. Take a look at what you did, and don't forget to make sure that you factor correctly, and also to remember to cancel out diagonally if you can, because some of these problems we would not get these answers if we did not cancel out diagonally. You can see that from this problem down here where we had to cancel out the 2c plus 1 and the 2c plus 1. Also, make sure you look out for GCFs, because sometimes GCFs will be what allows you to factor a little bit more than you could otherwise. And there's some more GCFs in several of the other problems. Finally, don't forget about difference of squares, as you can see in this problem here. And also remember that you don't have to factor if you have a linear function like this one right here. So if there's no squared, you're not going to do anything except for a GCF possibly. Now, division, if you have forgotten how to divide fractions, if I have 2 divided by 1/2, we can divide by a fraction by changing that into a multiplication problem, but flipping the second fraction. It's called multiplying by the reciprocal. Then we just multiply like normal. We multiply the tops and we multiply the bottoms, or the denominators. So we get 4 for this. So one silly way to remember that is to multiply by the reciprocal. When dividing fractions, don't ask why. Just flip the second and multiply. So if that helps you, awesome. So once you have done that step, we just do exactly what we've seen done in the previous problems. You keep the first one exactly the same, you flip the second one, and you simplify. Now in this problem, there's no factors that match on the top or the bottom, so all we can do is multiply across the top, multiply across the bottom. And we get c to the 6th, I made a mistake there, divided by d to the 6th. All right, in the next one, there is some factoring that we can do. Notice the difference of squares here. We have L minus 7 times L plus 7. Be careful with your L's. They can look like 1 sometimes. And L plus 6 divided by L minus 6. Now for the second fraction, I have to flip it before I multiply, but there's no factoring to do here. So I'm just going to write the L minus 6 up top and the L plus 7 on the bottom. Now remember, these are factors. They go together and you cannot cancel them out part by part. You have to cancel out the entire thing. You can cancel out diagonally, or you can cancel out top and bottom. Now here I have an L minus 6 and another L minus 6. That divide to give me 1. Here I have an L plus 7 and another L plus 7 diagonally. That divide to give me L, or just a 1. And the rest that I have here is going to be my answer. L minus 7 divided by L plus 6. Now try these last 4. They are a little bit more tricky, but you can factor all of these. Factor every single problem, and don't forget, when you finish factoring or while you're factoring, you can flip the second problem. In this first one, if we factor the first fraction, this is what we get. As I'm factoring the second fraction, I'm going to go ahead and move the bottom polynomial to the top and factor it. So that's a difference of squares, x plus and minus 5. And I'm going to move the top polynomial to the bottom and factor it. So I have x minus 5 and an x plus 1. And now I can simplify. Notice that we have the plus 5 here, and diagonally another plus 5 there. We also have a minus 5 here, and right on top a minus 5 there. And we have a minus 3 here and a minus 3 there. And the leftovers, the x plus 2 divided by the x plus 1. If you want to put these in parentheses, you can, but you don't have to. And here are the last 3 completely worked out for you. So double check the rest of your work and see if we have any questions to ask me tomorrow.